Young's geometry theorem 8 says that any line in the geometry is parallel to exactly two other lines. And I want to go through this proof very carefully because it's got a couple of things. First of all, like most proofs in geometry, it's a constructive proof. We have to make sure when we're building the construction that it's in general, that we're doing it for arbitrary elements, arbitrary objects. Okay, so first, and then we're also using this typical structure where if we need to prove exactly two, then we prove at least two first, and then at most two, usually using contradiction on the can't be more section of the proof. So let's try that. So our first claim is that there are at least two lines parallel to any line in Young's geometry, and we're going to do a constructive proof. So first thing, we need to make sure that we just take an arbitrary line, right? That's this part of the proof statement, right? It says that any line in Young's geometry is going to have at least two lines parallel to it. Okay, well, let's take an arbitrary line. And now for our construction, I'm going to need a couple of things. So I need a point that's not on the line. You'll see why in just a minute. Let's talk about why that's true, right? Young's theorem 1 says there exist at least 4 points. We haven't used Axiom 3 much. Axiom 3 says that not all points are on the same line. So if I know that there are 4 points, and I know that not all points are on the same line, then I know that there is some P out there that's not on L. So now what we're going to do is we're constructing a line on P that intersects L. Why? Well, we're actually going to use P and Q as points for our Axiom 5 that says we can find parallel lines using a line L and a point P not on it. There exists exactly one parallel line that's parallel to L. And we can flip it around and do that for Q as well. So there are two parallel lines. We have parallel lines M and N. And just for clarity, we're saying that P is on line M and Q is N, and Q is on line M. And again, the whole plan was to use Axiom 5. Okay? Well, not a problem, right? We know that we've got two points that aren't on L, and we know that this theorem is true. Now the question is, how do we know that these two lines don't intersect? Well, we know that two lines parallel to a third line are parallel to each other. We've proven that already. All right, so, and that's not really that important for proving what we need to. So now we're going to show that there are at most two lines parallel to any line in Young's geometry. And I need to get rid of my pictures so we can see more down here. So the first thing we're going to do is note that we're proceeding by contradiction, as usual. I'm going to assume that a third parallel line, right? This red line over here is the third parallel line. It's parallel to L, okay? And so we're going to assume that it exists, and we're going to look for a contradiction. Okay, well, let's use Axiom 2 and Theorem 6. What's Theorem 6? Theorem 6 says that, well, hang on a second. Let's use Young's geometry Axiom 2. So lines L, M, and N are all on 3 points, right? So what we're saying there is that all of these lines have 3 points on them, right? 3 points on N, 3 points on M, and 3 points on L. Okay, so that means we've accounted for 9 points in the geometry, right? And what does Young's theorem 6 say? It says that two lines parallel to the same line are parallel to each other. So we know that N doesn't share any points with L, and we know that M doesn't share any points with L. But how do we know that M and N don't share any points with each other? Well, Theorem 6. That means that these 3 lines are accounting for 9 points. Well, that's all the points we have. So the third parallel line cannot contain any points on L, M, and N. And why not? Well, Axiom 4 says that you can't have more than, that for any 2 points there's a unique line, right? So if I had something like this, then we're going to end up violating Axiom 2 or Theorem 6, which says 2 lines parallel to each other, parallel to the same line, have to be parallel to each other. So combined, they give us the fact that this line can include multiple points over here. And anyway, it doesn't matter because we're going to have at least a 10th point in the geometry, which is a contradiction. We can only have 9. So therefore, there's at most 2 lines parallel to any line in Young's geometry. So now claims 1 and claims 1 and 2 are true. But let's finish this off with some clarity. Right? Remember the structure of the proof. We have to start off, we're asked to prove that any line has some property. So the way we do that is that we let a line be arbitrary. And now at the end of the proof, since everything is true in claims 1 and 2, because the line L was arbitrary, right, both of these claims are true for every possible line I can draw in Young's geometry. Okay, so now we're saying, hey, we've proven that you pick any line L that you want, and the same proof will work. Okay. And therefore, any line in Young's geometry will be parallel to exactly 2 other lines. So I did want to go over this structure. It's an important one that we use all the time, and I wanted to be very clear on it. Also, this is a nice proof because while it's not all that hard, it does seem like it has a lot of steps, but this is pretty typical for the number of steps in a geometry proof. And I wanted to show you kind of how to lay this out so that everything is covered with precision and accuracy and completeness. I also want to show that this is true in other settings. So let's jump over to our little Young's geometry playground that I have here, and let's say, hey, maybe this point P that we have, right? Maybe this point P, what if we had it intersect with a different line, right? What if we had it intersect with L using this line? Is the same stuff still true? Well, I believe so, but here are the 2 points that are on the line, P and Q, right? So we could just write P over here and Q over here. So we have them. And then what do we need something that's parallel here. So line 10 goes through P and is parallel to L, and line 12 here goes through Q and is parallel to L. So you're like, well, that wasn't really impressive. It's the same 2 parallel lines as before. It doesn't always have to be. For example, what if we connected P to the line L? Remember, this is the line L over here, the green line L. The diagonal is the green line L. And suppose we connected P to line L. Remember, this isn't an intersection. This is where it connects over here. Now I have to find a line through Q that is also parallel, which you can see is line 12. And remember, these are not intersecting. Oh wait, I've got the wrong one because this is an intersection. This is an intersection of what I don't need. So I need something that goes through Q that doesn't, oh wait, that doesn't intersect P or Q. Hang on. Sorry, it's the same 2 as before. But I think you can get the idea that, for example, let me ditch these. Let's just look at lines 1, 2, and 3. Suppose that those were the only lines we have, right? And if the top one is line L, then there are exactly two others that are parallel to it, right? And then there's these are easy to see. It's only hard to see that there have to be two parallel lines when you pick up one of these diagonals, right? One of the diagonals makes it a little more difficult because you're going to have to use parallel lines down here to see where the two parallel lines are. And it's even a little awkward if you're stuck looking at one of these, like, oh, what's parallel to it? Well, one of the diagonals will be, and then what else is parallel to it? Well, probably one of the other curvy lines in the geometry. So again, I just was going through this to show you that we did indeed prove the theorem. Even though I'm using this diagonal, it'll work exactly the same no matter how I choose the initial line L.